Hello, everyone, and welcome to CloudAEye's webinar series, How to Become a Data-Driven Enterprise with AI. And previously we had two episodes, and we are having our third episode. And we are having a little bit of a change here in the sense that we have divided our 30-minute episodes into three smaller chunks of 10 minutes each. And today we'll be talking about classification models. So a quick recap, right? So in our previous episodes, we have talked about data-driven enterprise, and we have talked about AI concepts, and we showed some coding examples. In our episode 2, we had a deep dive into supervised machine learning models. If you recall, we talked about regression and classification as supervised tasks, and we also talked about why we should do train and test split of the data so that we can build our model on the trained data and then we can test it. And we also talked about some of the model fitting concepts that we all should be careful about, namely the bias and variance and overfitting of the models. Okay, and then we also looked into some ideas of how we can define a loss function, and how can we use regularization to check the overfitting of the models. And then we also looked into some coding examples for a detailed linear regression model. For this episode 3, as we have stated earlier, that we'll be dividing it into three small chunks. In episode 3A, which is this particular episode, we'll be talking about classification, and most importantly, we'll be talking about one of the most widely used classification models, namely the logistic regression model. And we'll try to give the idea of why we need such a model, and why linear regression models that we have seen before fall short of tackling this type of issues. So in this episode, we'll be going deep into the logistic regression model and how we can build it. And in the next episode, episode 3B, we will be working on a detailed coding example of logistic regression. We'll be doing code walkthrough and explanation. And in episode 3C, we'll be talking about the practical aspects of logistic regression, right? So when you build logistic regression model, what other things you should be careful about, right? How do you interpret the models? What does the different coefficients of the models actually mean? And how do you evaluate this model? Meaning that when you build a model, how do you know that your model is good? Okay, so that's the overall outline for the entire episode 3. And let's get into our today's agenda. So just a quick recap of what we have done before. That in the supervised machine learning model, if you remember, right, that there are two classes that we talked about. Regression, where we have the features and our output variable is actually a continuous variable. For example, we are trying to predict income or housing price or some numbers that are actually in a continuous scale, as opposed to classification, which we'll focus today. Okay, in classification, where the output variable, the y, right, in a supervised learning model, we have the inputs and outputs. The output in this case is actually discrete. Okay, and such examples of such models are logistic regression, decision trees, SVM, KN, and deep networks, so which we'll see in our subsequent episodes. Okay, in the last episode, we have also seen the need for breaking down the available data into train and test. Okay, usually we do a 80-20 split so that our models are not biased by looking into the test data set. So we build our model on training data, and then what a model means, right? So in a machine learning algorithm, we said that there are inputs and output, and we usually represent the output variable y as a function of the input, right? And that function f is what we call the model. and that model is parameterized by some coefficients or what we call weights in some models, right? So basically the relationship between the input and the output is learned through a function. Okay, so we have seen examples of a linear regression. So in the case, linear regression is the function, and then we learn it through some more coefficients. In this our case, we call them beta 0, beta 1, beta n, right? So this is the thing that we have looked into previously, and then we have also seen how a linear regression model is fit. We have discussed before that classification models are very different in the sense that their output variable is not continuous. So what we have done in linear regression is not actually suitable for classification type of things. Why? Because classification output is discrete values. So linear regression outputs are actually not necessarily bounded between 0 and 1 so that we can convert it into a classification type of thing, right? So as you can see in this example here, that if we have some data set that represents class 0 and class 1, and if we try to fit a linear regression line, then the line actually is not suitable for making classification. So what we do in this case takes into a linear regression output and pass it through some sort of a squashing function. So the line that we have seen before, right? Now we pass it through a squashing function, what we call a sigmoid function in this case, or a logistic function, which is usually has the signature of 1 over 1 plus e to the power negative z, right? So that is the function that we use for logistic regression. So to think of it this way, that we are still using the parameterization is very similar to the linear regression model. So we are representing the relationship between the input and output as a function of these parameters, right? Beta 0, or in this case I'm using W0, W1, right? So you'll see in different books or in different places they use these terms interchangeably, right? Beta or W, they all means parameters or weights. So what we are doing here is that we are using the exact same like model parameterization, but we are passing it through the sigmoid function. So previously, when we look into our linear regression model, our model was straight y equals beta 0 plus beta 1 plus all of these coefficients, right? Here, instead of doing that, we are passing it through this sigmoid function, so that instead of this line, we are having this S-shaped curve, okay? And once we fit this model, right, the sigmoid function provides a score between 0 and 1, and we can use the score to define a threshold, okay? And then from that threshold, we can build a classifier. So how do we do that? So basically, this sigmoid function gives us a sort of a probability like distribution. So it is bounded between 0 and 1. And then we define a threshold. Most commonly used threshold is 0.5. So we said that, okay, so if our output, the sigmoid output is less than 0.5, then make it a class, make prediction of class 0. If not, like if it's more than 0.5, then make it a class 1. Thus, the threshold converts the output of logistic regression into a classifier, right? Then we will move on to the whiteboard. So in linear regression, what we had y equals beta 0 plus beta 1 x1 plus beta 2 x2 if we had n features, right? And then in logistic regression, and then this we know that, right, for this actually is a line or a linear relationship, although it's not that simple, but I'm just showing it simply. And in logistic regression, what we're doing is that we are saying this y is, and then if we call very simply just beta transpose x, right? This can be represented beta transpose x. We are saying this is the sigmoid of beta transpose x, such that instead of this line, we have this S-shaped curve that I have just shown you, which goes through, which is bounded between 0 and 1, and then, right? And then we say that if we put a threshold here. We put a threshold like this, and then we said, okay, if 0.5 is the threshold, if the value is in this domain, then we predict as class 1. If the value is in this domain, right, then we say it's class 0. Now, how do we get to this thing, right? So in logistic regression, or in statistics, there is a very like a well-known term that we used. Okay, that's called odds ratio. I'm coming to that in a second. Let's say we're doing a binary classification, and then we have two classes, right? Class y equal to 0 and y equal to 1, right? If these are these two classes, then we can say, like in terms of probability, you can say the probability of seeing my output equal to 0 given all my features. Okay, let's call it probability is p. Then probability of y equal to 1 given my features would be, let's call it p1 and let's call it p2. And we know that this probabilities are sums to 1. So basically this we can call p, and this we can call 1 minus p. If this is the case, then the odds ratio of these two classes, right, is called p divided by 1 minus p. And under the logistic regression term, we call it a term called log odds. Okay, so this is called odds. So odds ratio is used in lot of statistical terminologies in betting and in game, in like Vegas betting or other cases. We use the term odds ratio a lot, right? So the similar thing, we now say that log odds, in case of logistic regression, we say that log of the odds is actually beta transpose x. So if we use this, we can actually say that log of p over 1 minus p is beta transpose x. And one can actually do very simple algebra to find that p, which is in our case is the model output, right, is equal to 1 over 1 plus e to the power negative beta transpose x. And the other one would be 1 minus p. So this is the actual derivation of the logistic regression, right? So in our next episode, we will take a look at an example of how we can apply logistic regression in classification data. All right. Thank you.